Right now, you are pulling on the Earth. That is not a joke. Everything pulls on everything else. That is the whole idea. It is called universal gravitation. Universal just means everything. No exceptions. You and the Earth and the Moon. You and the person sitting next to you. But hold on. If the person next to you is pulling on you, why are you not sliding toward them? Because this pull is unbelievably weak. You and that person really are pulling on each other. The pull is there. It is just far too small to feel. Here is how small. Two people standing a meter apart pull on each other with a force worth about 0.03 of a milligram, 1/30,000th of the weight of a paperclip. Your body will never notice that. Nothing will. 111 years after Newton first published this rule, Henry Cavendish finally managed to measure that pull between two ordinary objects, two small lead balls hanging from a thin wire, two huge lead balls brought close, 348 pounds each. The small balls leaned over. Barely. Moving air would have wrecked it, so Cavendish sealed the room, moved the weights with ropes from outside, and watched through a telescope. A sealed room and a telescope to see the pull between two lumps of metal. And yet, take this weak little force away and nothing holds together. You would not fall off the Earth. There would be no Earth. The planet is a ball in the first place because this force pulled the pieces into one. So here is Newton's rule, written the way we write it today. Newton himself wrote it out in words, not symbols. That letter at the front, G, was added more than a century after he died. It is the number for how weak this force is. Newton never knew its size. It only arrived after Cavendish sat in that sealed room. So if the pull is that weak, why does the Earth yank you down so hard? Because the Earth is absurdly large. The pull depends on how much stuff each thing is made of. That is what mass means. How much stuff. And the way it depends is simple. Take one apple hanging on a tree. The Earth pulls it with a certain force. Hang 2 apples. Twice the force. 3 apples, 3 times. More stuff, more pull. Straight down the line. Now the same thing is true of the other side. If the Earth had twice as much stuff in it, it would pull twice as hard. Each side raises the pull on its own, so you multiply the two together. And one of those two numbers is the entire Earth. That is how a force this feeble still holds you down. Here is the strange part. You are pulling the Earth upward exactly as hard as it pulls you down. Exactly as hard. The Earth just does not budge. There is far too much of it to move. Then something is wrong. The Sun has 330,000 times more stuff in it than the Earth does. By that rule, the Sun should be pulling you far harder than the ground under your feet. You should be flying up into the sky right now. You are not. So the amount of stuff cannot be the whole story. What is missing is distance. The Sun is very far away. So how much does distance take away? In January of 1684, 3 men were arguing about exactly that in a London coffee house. Edmund Halley, who would later work out when a certain comet was coming back, which is why that comet carries his name today. Robert Hooke, who put cork under a microscope and named the cell. And Christopher Wren, the architect rebuilding St. Paul's Cathedral after London burned down. All 3 suspected the same answer. Move twice as far away, and the pull drops to a quarter. Not a half. A quarter. Here is why. Picture the pull as spray paint, pushed out from one spot in every direction at once. At any distance, that spray has to cover the whole outside of a ball. Go twice as far, and the ball you have to cover has 4 times the surface. Same paint, 4 times the wall. The coat goes 4 times thinner. Careful with the picture, though. The pull is not paint. It never runs out. It only spreads. All 3 men had that much. What none of them could do was prove what it meant for the path of a planet. So Wren offered a prize. A book worth 40 shillings to whoever proved it inside 2 months. Nobody claimed it. That August, Halley rode to Cambridge to ask a man who kept to himself, if the pull thins out like that, what shape is a planet's path? The man answered right away. An ellipse, a stretched circle. Halley was stunned. How could he know that? I have calculated it, the man said. Then he started going through the papers on his desk, looking for the sheet with the working on it. He could not find it. The man was Isaac Newton. He could answer that fast because he had already worked the mathematics out years earlier and then put it away without telling anyone. And he had one more reason to trust the rule. He had already tested it against the moon. That test goes like this. Drop an apple near the ground. Every second, it speeds up by 9.8 meters per second. The moon sits 60 times farther from the center of the Earth than that apple does. 60 times 60 is 3,600, so the moon should be pulled 3,600 times more gently. 9.8 divided by 3,600 gives 0.0027, which is almost nothing. It means the moon speeds up by less than 3 millimeters per second every second. That is the prediction. Now go and check it against the real moon. How do you check it? You already know two things about the moon: how far away it is, which people had known roughly since the ancient Greeks, and how long it takes to go around once. 27 days and a bit. Anyone can count that from a window. Those two numbers alone tell you how fast the moon is curving toward us. The answer is 0.0027. The same number, the force that drops an apple and the force that holds the moon, are one force. Understand what that broke. Until then, people believed the sky and the ground were two different places running on two different sets of rules. Down here, things fall. Up there, lights go around forever in perfect circles. Nobody expected the two to have anything to do with each other. One matching number erased that wall. The sky runs on the same rule as a dropped apple. That check had a weak link in it. Look again at what it needs. It needs the size of the Earth. Because the moon's distance was never known on its own. It was known as a multiple of the Earth, 60 Earths out, roughly. So get the size of the Earth wrong, and the moon's distance goes wrong with it, and the whole check goes soft. The value Newton had was too small. It came to him second-hand from sailors and mapmakers. Then a French astronomer named Jean Picard surveyed a stretch of France properly and measured the Earth again. With that better number in hand, the check came out tight. The idea had been right the whole time. What was shaky was a number somebody else had measured. Being right is not enough. Somebody has to be able to measure too. If the Earth is pulling the moon this whole time, why has the moon not come down on our heads? It is coming down. It has been falling this entire time. Newton drew the answer himself. Put a cannon on top of a mountain so tall it stands above the air. Fire it gently and the ball lands nearby. Fire harder and it lands farther away. Now remember, the Earth is round. While the ball flies forward, the ground underneath it is curving away downward. Fire hard enough, and the ball drops by exactly as much as the ground drops away. So it never gets any closer to the ground. It misses the Earth, over and over, forever. That is what the moon is doing. The moon is falling toward us the whole time. It is also moving sideways, fast, so it keeps falling past us instead of into us. Fall, miss. Fall, miss. Do that all the way around and you have a loop. That is an orbit. Falling forever without ever landing. And the exact shape of that loop, once you work it out, is a stretched circle, an ellipse, which is the answer Halley rode to Cambridge to get. One thing in all of this was quietly cheating, and Newton knew it. We keep saying distance. Distance from what? The Earth is not a dot. The dirt under your shoes is 1 meter away from you. The dirt on the far side of the planet is 12,000 kilometers away. Every one of those pieces is pulling on you, and everyone sits at a different distance. To be honest about it, you would have to add up billions of separate pulls, each one weakened by its own distance. Newton did that sum, and the answer came out beautifully simple. Add all of it up, and a solid ball pulls on you exactly as if every bit of its stuff was squeezed into one point at the dead center. That is why we measure from the center. That is why the moon was 60 times farther out, 60 times the distance from the center. This proof is not easy, and it is a big reason the book took as long as it did. Halley did not let that lost sheet of paper go. He went back. He kept after Newton, kept asking, kept him at it, until the calculation was written out again, properly, from the beginning. What came out the other end was the Principia. Philosophiae Naturalis, Principia Mathematica, arguably the most important science book ever printed. And then the Royal Society could not pay to print it. They had spent the year's budget on a lavishly illustrated book about fish, so Halley paid for the Principia himself out of his own pocket. One question never got answered. Why does stuff pull on stuff at all? Newton did not know. He said so out loud, in print, and refused to invent a reason. What he worked out instead was how much. Just how much. And how much turned out to be enough. Enough to put the apple, the moon, and every planet under one rule, with nothing left over. The force holding you in your chair, the force holding the moon in the sky, the force keeping the earth beside the sun. One force. Only the amounts are different. That is what universal means. No exceptions. 200 years later, Einstein answered the why, and answered it very differently. Newton's rule still flies the rockets,